Imagine you're floating in space. Not the romantic kind you see in movies. The real kind. Cold, silent, absolute. And somewhere ahead of you, not visible, not glowing, not dramatic, is something that has already decided your fate. You don't see it coming. That's the first thing most people get wrong about black holes. They imagine a swirling drain, a glowing ring, something you could recognize and avoid. But the most dangerous ones give you no warning at all. No light bends, no alarm sounds, no physical sensation. You simply cross a line that exists only in mathematics. And everything changes. Scientists call it the event horizon. And once you're past it, the universe you knew is gone. Not destroyed, not erased. Just permanently behind you. Unreachable. What happens next is where physics stops being comfortable. Because the story of what a black hole actually does to a human body, to time itself, to space, to the very fabric of reality around you, is not what anyone expected when they first ran the numbers. Some of it is deeply counterintuitive. Some of it is deeply disturbing. And some of it rewrites the way you think about existence entirely. This is not a thought experiment. This is what the science actually says. And it's stranger than anything fiction has ever tried to imagine. Let's start with something most textbooks skip. A black hole doesn't pull you in the way gravity pulls you toward the ground. It's not a tug, not a drag. It's more like the entire geometry of space around you begins tilting. Every direction, forward, backward, left, right, slowly starts pointing toward the same place. Toward the center. And the terrifying part, you can't feel it happening. In 1974, physicist Stephen Hawking sat with his calculations for 3 straight days. He kept getting the same result. He checked it again. And again. The answer didn't change. What he found wasn't just strange. It quietly dismantled something scientists had assumed was permanent. But we'll get to that. First, the fall itself. If you were somehow positioned at a safe distance from a stellar mass black hole and began drifting toward it, the initial experience would be almost peaceful. No sound, no visible distortion, no dramatic warping of light. Just silence, and a very slow, barely noticeable acceleration. For hours, possibly days depending on the black hole's size, nothing would seem wrong. That's what makes it so disorienting when researchers first modeled it. The danger is invisible until it's absolute. But here's where it gets complicated. Someone watching you from a distance, say from a spacecraft far away, would see something completely different. They wouldn't see you fall in. They'd see you slow down. Freeze, hang suspended at the edge of the horizon for what appears to them to be an eternity. 2 people, same event, completely opposite experiences. And that contradiction sits at the heart of something far darker. That contradiction has a name. Physicists call it time dilation. And it's not a metaphor, it's not poetic language. It is a measurable, documented, experimentally confirmed feature of our universe. Time itself moves at different speeds depending on where you are and how strong gravity is around you. We've proven this on Earth. GPS satellites have to be constantly corrected because time runs slightly faster in orbit than it does on the ground. Remove that correction, the satellites stop working. That's not theory, that's engineering. Now scale that effect to something with the gravitational force of 1 million suns compressed into a single point. The numbers stop being subtle. They become extreme. For the man falling into the black hole, time flows normally. He checks his watch, seconds pass like seconds. He feels nothing unusual. But for the man watching from the distant spacecraft, his colleague, his mission partner, the one holding their breath at the observation window, time for the falling man appears to nearly stop. He watches him slow, watches every movement stretch. A hand raised in what might be a final signal takes hours to complete. Then days. Then the image fades, not because the man disappears, but because the light carrying his image gets stretched so severely it shifts out of visible range. He doesn't see him die. He doesn't see anything conclusive at all. He just watches him become dimmer. and dimmer, until there is nothing. That absence, that unresolved image, is one of the most psychologically disturbing outcomes researchers didn't anticipate when they first built these models. You never get confirmation. You never get closure. But what happens to the man still falling? That's where the science takes a turn nobody was prepared for. From the inside, the fall continues. No alarm, no pain, no dramatic shift. Just the slow, steady acceleration of a man moving towards something he cannot see and cannot stop. For a black hole massive enough, and some of them are genuinely incomprehensible in scale, the event horizon could be crossed without any physical sensation whatsoever. No jolt, no signal, no warning from the universe. You would simply be inside, and you wouldn't know it. That detail alone kept several physicists awake for a long time after they first confirmed it. Because it means the most significant boundary in the known universe, the point of no return, is completely invisible. No surface, no wall, no edge you can touch or see or feel. Just a mathematical threshold hanging in empty space. Crossed in silence. Now here is where the human body begins to matter. Because gravity, even stretched across something enormous, is not perfectly uniform. The side of your body closest to the singularity, the central point, experiences slightly stronger gravitational pull than the side furthest away. That difference is called a tidal force. On Earth, tidal forces are gentle, they move oceans. Inside a black hole's grip, they become something else entirely. The differential pull begins stretching whatever it touches. Scientists have a clinical word for what happens to a human body under those conditions. Spaghettification. It sounds almost absurd. It is anything but. The process is slow at first, imperceptible. Then it isn't. But here's what the models revealed that no one initially expected. The timing of when this begins depends entirely on something outside the victim's control. Something determined long before he ever got close. The size of the black hole determines everything. That's the detail that changes the entire picture. A smaller black hole stellar mass, the kind formed when a single massive star collapses, has an event horizon that sits very close to its singularity, which means the tidal forces near that horizon are already extreme. Cross that threshold and spaghettification begins almost immediately. The body doesn't get time to process what's happening. It simply begins to elongate, atoms pulled in directions they were never designed to travel. But a supermassive black hole, the kind sitting at the center of entire galaxies, some with masses billions of times greater than our sun, tells a completely different story. Their event horizons are so vast, so geometrically enormous, that tidal forces at the boundary are relatively mild. You could cross the point of no return in one piece, completely intact, possibly unaware. And for a period of time, minutes, perhaps hours depending on the mass, you would continue falling freely. Conscious, breathing, thinking. Trapped inside something you cannot escape, with no external signal reaching you and no way to communicate that information outward. Whatever you experience from that point forward stays there forever. That permanence is what struck Dr. Kip Thorne, the Nobel Prize-winning physicist who spent decades modeling these scenarios, as the most quietly devastating aspect of the whole equation. Not the destruction, the isolation, the absolute physics-enforced silence of what comes after the horizon. But the destruction does come. And when researchers finally mapped the full sequence, moment by moment, force by force, one stage of the process stood out as uniquely disturbing. Something that happens long before the singularity is reached. The stage researchers kept returning to wasn't the final destruction. It was the moment just before it. As the falling man accelerates deeper into the black hole's interior, the tidal forces begin their work gradually. First, an almost undetectable stretching along the vertical axis. The body elongates millimeters, then centimeters, while simultaneously being compressed from the sides. The circulatory system feels it first. Blood begins pooling in directions gravity is pulling hardest. Pressure builds in ways the human body has no biological response for. No reflex, no adaptation, no survival mechanism that evolution ever needed to develop. Because nothing in the history of life on Earth ever needed to survive this. Then the nervous system, signals that normally travel cleanly from brain to body, begin distorting under the spatial compression. Researchers who modeled the neuroscience of this process noted something that stopped the room during a 2019 conference presentation. In the final conscious moments, depending on the size of the black hole and the speed of descent, the brain may still be functioning, processing, receiving signals, aware, not of pain necessarily. The nervous system may not have a framework to interpret what's happening as pain, but aware of something being profoundly, irreversibly wrong. That window of awareness, however brief, represents the most isolated moment any human being could theoretically experience. Cut off from every other human, every signal, every possible rescue. With the entire observable universe now permanently on the other side of a boundary that cannot be crossed. And then, silence. The body ceases as a unified structure. But here is what Hawking's original calculation, the one he checked 3 times in 1974, actually revealed about what happens next. It changes everything we thought we understood about where the information goes. Hawking's calculation revealed something that should not have been possible. Black holes leak. Not matter, not light, nothing that violates what we already knew. But energy. Slowly, imperceptibly, over timescales so vast they make the current age of the universe look like a brief introduction. He called it thermal radiation. The world came to call it Hawking radiation. And when the physics community first received his paper in 1974, several leading scientists assumed he had made an error. They checked his mathematics. They couldn't find one. What Hawking had discovered was that the boundary of a black hole, the event horizon, is not perfectly still. At the quantum level, pairs of particles constantly flicker into existence everywhere in space. Normally, they annihilate each other instantly. But at the edge of an event horizon, one particle falls in while the other escapes. The escaping particle carries energy outward. The black hole pays for it. Over an almost incomprehensible stretch of time, this process slowly drains the black hole's mass. Smaller black holes evaporate faster. Supermassive ones would take longer than the current age of the universe, multiplied by numbers that have no meaningful human reference point. But they do evaporate. Eventually. And this is where the real problem emerged. The one that divided the physics community for nearly 5 decades. The one Stephen Hawking and John Preskill famously debated in a public wager that ran from 1997 to 2004. If the black hole eventually evaporates completely, what happens to everything it consumed? What happens to the man who fell in? The atoms, the molecules, the information that made him specifically him. Does it survive in some form? Or does the universe simply erase it? In physics, information is everything. Not information in the casual sense, not memories or feelings or identity. Information in the precise, technical sense. The exact quantum state of every particle that makes up a system. The position, the spin, the momentum. Every measurable property of every atom. Physics has a foundational principle built around this. It states that information cannot be destroyed. Ever. It can be scrambled, encoded, transformed beyond any practical recognition. But the universe keeps a record. Always. This principle, called the conservation of quantum information, underpins nearly every branch of modern physics. Remove it and the entire theoretical framework begins collapsing in ways that cannot be easily repaired. Which is exactly why Hawking's evaporating black hole created a crisis. If a black hole consumes matter, consumes a man, his atoms, his entire quantum history, and then slowly evaporates into featureless thermal radiation, that information is gone. Not scrambled, not encoded somewhere recoverable. Gone. Destroyed. Permanently. And that directly contradicts one of the most tested, most reliable principles in all of science. Hawking initially believed the information was simply lost. He defended that position for years. Other physicists, including Leonard Susskind and Gerard T. Hooft, both among the most respected theorists alive, said that was impossible. That Hawking had to be wrong. Not about the radiation, about what happens to the information. The argument grew. It spread across conferences, papers, private correspondence. It became known as the black hole information paradox, and it remained unsolved for decades, until a group of researchers began examining the event horizon itself far more closely. What they found there quietly rewrote the picture entirely. The event horizon was supposed to be empty. That was always the assumption. A mathematical boundary, an invisible line in space. Nothing physically special about it. Nothing you could touch or measure or detect. Just a threshold defined by geometry. But in 2012, a team of theoretical physicists led by Ahmed Olmeri at UC Santa Barbara ran the numbers on something nobody had fully calculated before. What quantum mechanics actually requires at the event horizon if information is truly preserved. The result stopped them cold. If information must escape the black hole encoded in the Hawking radiation, then the particles leaving the black hole cannot be in the quantum state everyone had assumed. They must be fundamentally different. And if they're fundamentally different, the event horizon cannot be empty. It must contain something. Something energetic, something real. Something with physical consequences for anything passing through it. They called it a firewall. A wall of high-energy radiation sitting precisely at the boundary of the black hole. Invisible from the outside, but lethal at the threshold. Which meant the man falling in, the one who felt nothing crossing the horizon, the one drifting peacefully through what appeared to be empty space, may not survive the crossing at all. Not from tidal forces deep inside. Not from the singularity. But from the boundary itself. Instantly, completely, at the very moment of crossing. The firewall hypothesis tore through the physics community. Because it didn't just challenge one assumption. It forced a choice between three principles, each one foundational, each one supported by decades of evidence. And only two of them could survive. The question of which one to sacrifice has not been answered yet. The three principles sitting in direct conflict are not minor theories. They are load-bearing walls of modern physics. The first is general relativity, Einstein's framework for how gravity shapes space and time. Tested, confirmed, used daily in GPS systems, satellite communications, astronomical calculations. It says the event horizon is smooth, empty, crossable without incident. The second is quantum mechanics, the framework governing how particles behave at the smallest scales. Equally tested, equally confirmed. It says information cannot be destroyed, ever. The third is the equivalence principle, the idea that a man in free fall cannot detect his own free fall through local measurements alone. That gravity and acceleration are indistinguishable. It sits at the very foundation of general relativity itself. All three are supported by overwhelming experimental evidence. All three cannot simultaneously be true near the event horizon. Something has to break. Physicists call this the AMPS paradox, named after Olmeri, Marolf, Polchinski, and Sully, the four researchers whose 2012 paper forced the contradiction into the open. Since then, every major theoretical physicist alive has taken a position. Some argue the firewall is real and general relativity simply fails at the horizon. Some argue information is somehow encoded on the horizon's surface in a way that doesn't require a firewall at all. Some argue both pictures are simultaneously valid, that the universe itself maintains two contradictory but self-consistent descriptions of the same event. That last proposal has a name: black hole complementarity, and it suggests something deeply unsettling about the nature of reality itself. Not just black holes. Reality, the idea that the universe may permit fundamentally incompatible truths to coexist, depending entirely on where you're standing when you observe them. Here is where we land, not with a clean answer, because there isn't one. Not yet. What we know with certainty is this. Black holes exist. We have photographed them. We have detected the gravitational waves produced when they collide. We have watched stars orbit the one sitting at the center of our own galaxy for decades. They are not theoretical anymore. They are real, present, active. The supermassive black hole at the center of the Milky Way, Sagittarius A, has a mass 4 million times greater than our Sun. It is approximately 26,000 light-years away. And it is doing exactly what black holes do. Quietly, continuously, without pause. What happens to a man who falls in remains, in the strictest scientific sense, unknown from the outside. The observer at the spacecraft window never gets confirmation. The image fades, the signal stops, the question stays open. From the inside, the science suggests a sequence that moves from peace to irreversible destruction across a timeline determined entirely by the black hole's mass. Crossing an invisible boundary without knowing. Drifting in absolute isolation. Then the forces arriving. Then silence, and somewhere encoded in the slow radiation bleeding from the horizon over timescales beyond human comprehension. Perhaps the information survives. Perhaps the universe keeps its record after all. Perhaps nothing is ever truly erased. We don't know. And that uncertainty, that honest, unresolved, physics-enforced uncertainty, is not a failure of science. It is science working exactly as it should, pushing toward the edge of what reality is willing to reveal, and finding that the edge is further than anyone expected. If that kind of question keeps you thinking, you know where to find the next one.